Okay, everybody, thank you for coming. First opportunity to be in this building, illustrious group of students, faculty, colleagues, etc. And today you're going to hear about technology, cybersecurity, and policy. Topology, I'm sorry. So, technology, cybersecurity, and policy. Technology, cybersecurity, and policy. And you're going to hear it in the context of space. Cybersecurity and space. And there are fundamental questions that you will all ask. What in the world does cybersecurity have to do with space? I mean, can't you just string a long copper wire from a satellite down to a ground station? I mean, these are all possibilities. But today the panel will give you a sense of technology, cybersecurity in space. So, without further ado, I'm going to introduce Wayne, who is our moderator. Wayne, you're our moderator. And so you're going to tell us why technology, cybersecurity, and policy are important, or at least the panelists will. So, everybody, please welcome our panelists, and please welcome Wayne.
Hi, thanks. So I'm going to run this fairly informal, so I think you can come in, panelists, myself, we'll give some inputs, but feel free to ask questions and so forth. And what I was going to do is I'll just do a quick introduction of myself, then I'll allow each of the panelists to introduce themselves and some of their background, and then back to me, I'll sort of frame the problem space and space and cyber where we're at, and then the panelists will provide inputs, and then we have some questions on specific areas and so forth. So my name is Wayne Wheeler. I'm a senior project leader at the Aerospace Corporation, which is the FFRDC, or Federally Funded Research Corporation for space. So our primary customer is the Air Force, of providing technical and acquisition consultation to the Air Force. Most of the work I'm currently doing has to do with resiliency of space systems against various threats, which includes cyber. And I also teach at UCLA in cloud and cyber classes. So.
Hi, I'm Ethan Pucciati. I'm a principal cyber architect with Lockheed Martin Space. Our business area, or at least our line of business, the one that I'm in the leadership role for, is military space. So we deal quite a bit with the Air Force. You may know many of our platforms, GPS, SIBRs, some of the other major constellations like Advanced EHF. I've been in cybersecurity for about 8 years. Including a little bit of my master's degree, and I have to say this topic is especially topical for me. My background was in aerospace engineering as a major, both bachelor's and master's, and then I transitioned into cybersecurity, so I've gotten to see both sides of the fence, and hope to contribute in this discussion.
Hey, good afternoon. I'm Erin Hanson. I'm actually an Air Force active duty officer, cyber warfare operations officer. I also kind of moonlight with TCP as a faculty and teaching penetration testing and digital forensics. My experience with penetration testing and securities goes back 15, 18 years, kind of even before cyber was called cyber, specifically focusing on network security. My focus areas right now are within forensics as well as critical infrastructure and ICS or SCADA type of systems.
Hi, my name's Keith Gremben. This is my third day as TCP faculty, so good to see all of you. Hopefully I'll get to recognize you in short order. So prior to coming here, I was with the Department of Commerce in those laboratories across Broadway, where I ran a laboratory called the Institute for Telecommunication Sciences, where we worried about spectrum management, spectrum vulnerability, and purposeful and inadvertent interference with mission-critical systems like Air Force radars, satellite uplink and downlinks, and so forth. So I'm interested at the physical layer of security.
My name is Eric Frew. I'm a professor here in the Aerospace Engineering Sciences Department. My research focuses on autonomous systems and field robotics with an emphasis on unmanned aircraft systems and taking them into the field for earth science applications. But a lot of the things we need to think about to make safe and secure unmanned aircraft also apply in the space domain. So I have some interest there as well.
Okay, great. So spacecraft and cyber, sort of how do they fit together? A lot of you probably don't have a very little exposure to the space domain, but it's one of those somewhat invisible things like the internet that's really a backbone from everything that we do, from GPS on our phones to lots of military applications to direct TV for users all over the world, those sorts of things. And it's an area that's in a lot of rapid transition, and so it makes it interesting and exciting if you like change, but it is challenging. There's probably on the range of a few thousand very high value assets in space that are running various missions. There's a lot of small sats, a lot more experimentation now, and you may have heard about Amazon and Google. Others are in the early stages of launching literally thousands, if not tens of thousands, of constellations of satellites for various comm missions and so forth into space. And so they titled this early section "A Day Without Space." If you pulled space out of the equation, you would definitely notice a lot of things would not work. A lot of trucks would not make deliveries. We wouldn't be able to find our way around, and so it would have a very high impact. Space systems, particularly the large high-value assets that cost maybe $1 billion in some cases, take a long time to design. They're very expensive to launch. They're very expensive to manage. And the model for the last several decades has been very successful in terms of mission safety, mission operations. They last a long time, but it's launch once, use 25 years. And if you launch once and use 25 years from a cyber standpoint, that's an entire lifetime. So you have a lot of things that are up there flying now that the word virus has no meaning when they were originally designed, except they may have vulnerabilities and so forth. So hence this whole discussion. A lot of us are spending our professional career right now looking directly at cyber as it relates to spacecraft, but it's a very concerning issue both for Department of Defense, commercial users, really everyone, because you can't just do your Patch Tuesday upload and, I don't like my tablet, it's vulnerable, I'll throw it away, buy a new one. That's not, even if you're doing a lot of more rapid launches, that's not the kind of environment it is. It's still launch once, use 10 years. And when you're in that kind of environment, you have to be much more involvable and so forth. So sort of input in the same question of how cyber generally relates to spacecraft.
Yeah, I can say for one of our big sticking points, at least at Lockheed Martin, has been how does cyber contribute to resiliency of the platform overall? And especially for our military customers, they want to understand, for things like GPS, how resilient is this related to certain threats? And one of those big threats, obviously, is cybersecurity as it's emerged over the last 15 or so years. And really, a common misconception is that cybersecurity is new. It's really not. If you look at the attack surface across, for instance, NASA and JPL and some of the other commercial organizations, and this is all data you can find in open source, cybersecurity threats are a mainstream thing for space, and they have been for a number of years. And really where it becomes interesting is the cyber-physical aspect, and that's something that we try to consider is when we look at cybersecurity as a threat, ultimately we're not just looking at the exfiltration of information or stealing information. We're really looking at cybersecurity as a threat to how does this platform continue to operate? How does this platform support all of the end users? And when you think about GPS, it's not just military end users, it's all of us. And the fact is that timing and navigation is a huge attack surface and a huge threat when we look at it from an information standpoint. So these are just several of the things that we consider throughout the engineering process. But I think the real key takeaway from our perspective is that cyber is a lot more than just dealing with information. It really is extending into the physical domain, and especially when we talk about platforms, whether that's space or air or other types of platforms that have to perform certain functions.
You just pass on down. That'd be fine.
We're all taking a crack at this one?
Yep.
Okay. I would say we could even think about it in a pure basic format as regardless of the system, whether it's a space system or any other type of network, it all breaks down to links and nodes. So given the fact that there's communications traveling across these links in between these nodes, the communications medium is irrelevant. It doesn't matter whether it's wired or wireless. The fact that it communicates introduces potential vulnerabilities within that system, whether that's interception, modification, injection, disruption type of attacks. So the fact that the space is what we're talking about today, the geography, the distance between a ground station and an asset that's overhead, yeah, there's some distance there, but if we think about it in that basic form, it's still a link and a node. So any vulnerabilities that could be introduced into a traditional wired network could potentially be introduced into this type of system or system of systems.
And so one of the obvious factors about space is there's no wire connecting you to your assets, right? So everything you're communicating is available to anybody who's got the right receiver to listen in. And so, one of my concerns is what's being done to secure the links on all these wireless devices that we're increasingly dependent on. They can be jammed, they can be spoofed, they can be sniffed, and you want to be able to protect your data. So, in particular with GPS, there's a number of public papers out there of people who have spoofed GPS and led yachts to a different island in the Mediterranean that it was heading for, and the crew didn't know it was happening because they were trusting their GPS. And so how many other vulnerabilities are we introducing as we become more dependent on small-scale constellations of space systems? And we need to be thinking about securing these systems and securing the links from the very beginning of the design stage, not afterwards when we figure out, oops.
And I'll just expand on that a little bit. And we're talking about cybersecurity as it relates to space, but keep in mind that space is maybe the anchor, right? We're thinking of spacecraft that are orbiting, but those spacecraft are commanded and controlled from the ground, and perhaps the cybersecurity is about the command center that we're using to control our GPS constellation, or perhaps it's about the devices on the ground, the GPS receivers that receive that information. So even though space is sort of the physical location that is central to this discussion, cybersecurity of those assets is a much bigger picture. A lot of the computer networking problems, the RF communication problems, the human engineering, the social engineering problems of the command centers all still apply to space. So it's both a unique domain and it's very similar to many other domains that we would talk about for cybersecurity.
Okay. Next thing I thought we could talk about is what kinds of classes of vulnerabilities we're really talking about as spacecraft. Again, if you don't have a background in it, spacecraft are not Windows 10, right? You're generally running some sort of real-time operating system. It's probably older. You're maybe running some code that's older. A lot of you are in school now, languages you probably, Fortran, some things you may even hardly have heard of that you can find on, running a lot of spacecraft systems. However, just because a star tracker just has a primitive PROM device on it or some kind of embedded device doesn't mean it's not cyber and doesn't mean it couldn't be vulnerable because it's code. There's code everywhere. There's firmware, there's hardware, there's embedded devices. And so spacecraft are very complex. They have thousands of devices from thousands of sources and subcontractors, star trackers and sensors and propulsion units, and there's a very extensive and complex supply chain for all these parts, and so there's a lot of concern of how do you sort of grab all that back, and Lockheed, especially from a contractor's standpoint, they're really concerned about, well, we're buying all these parts, how do we know they're safe parts and so forth. And so as a cyber physical system, cyber can move from code into physical. In other words, you can break things by cyber. Bad things can happen because you can command them via cyber. So maybe the other panelists would like to talk a little bit about what it really means to be cyber physical and what terms like malware and stuff would mean in space. So we can just You can start that end, that's fine.
Well, I mean, I guess I'll just sort of start with some of the obvious issues. And again, drawing on parallels with my own work in drones, like if you're not thinking about the links, if you're not encrypting your links, you can just spoof the commands, right? I mean, we're seeing more and more small satellites launched by universities, systems that aren't necessarily big DoD spacecraft, and if they're broadcasting and you can hear them, you can talk to them. So just the very basics, you know, it seems, again, it's worth repeating. Do the simplest things first. Make sure that not everybody that has a ham radio can talk to your spacecraft, can figure out the command structure, can send the commands back. If you can do that, the rest of the stuff doesn't even matter, right? And I tell you, that was the issue with drones for a long time. Finally, we're starting to encrypt the links, but start from the very basics from the very beginning and then build to the more complicated things.
You know, one of the interesting things that's happening in space right now is the rise of, you know, with the CubeSat, and space assets are now becoming available to small companies. And so small companies have this pressure of time to market, right? If I've got a great idea, I need to get it out there on the market before that guy down the street gets it on the market, or I'm out of business. And so they've got to deal with this trade-off between, do I get the time to market and cut on the security, because that's going to cost me more money and time? But then you've got to remember, you're creating a vulnerability that, you know, in the end may do your company less good than being the first on the market was.
I kind of want to approach this from an adversarial standpoint. So how would the adversary think about maybe attacking or targeting some of these systems, especially if they're legacy systems that are decades old? They were designed to receive an input, and if the system did not receive and act on that input, then it was considered faulty. And when companies and corporations are monetizing this, they want to make sure that this thing can receive the input and execute any instruction it's given, because that's what it was designed to do. So if I'm thinking about this from an adversary standpoint, and this could be anybody with some RF equipment that's powerful enough to reach a couple hundred miles into orbit, or a nation state, it becomes very easy for them to potentially attack, disrupt, inject this type of system and prevent those communications, maybe give different types of signals for the asset to execute. So that can definitely change the parameters a little bit. I think the barrier to entry for an attack on this type of system is very, very low. It could be something as simple as fuzzing in a direction on a given frequency, and that could have some effects that either the owner of the asset or even the attacker doesn't even realize. So I'll just leave it with that one.
Yeah, you brought up a good point too. With with older legacy systems, a lot of it is about trust, right? And how our trust model has changed over time. With a number of embedded systems, what we've typically found is that inputs in most cases are considered trusted, that the data that is going in is coming from a place that it should be coming from, and that it's coming from an entity and that is part of that trust boundary. And one of the interesting things is, in looking at kind of the vulnerabilities and attack surface for space and embedded systems in general, is it does center around trust and some of the classes of vulnerabilities that you'll see are, weak authentication, lack of encryption, those things that we kind of take for granted when we look at it from an enterprise IT standpoint, comparing that to embedded. And then one of the other interesting points when you talk about space and the architectures in general is just that you've got all these dependencies across multiple system types. We brought it up as system of systems, really, that there's a ground system that is involved in the command and control channel, as well as monitoring the spacecraft. That presents attack surface. And Wayne mentioned supply chain. That's a huge challenge in terms of how do we know that the components themselves aren't compromised before we even get to the launch point or before we even get into space. And then you talk about software and code and how a development environment contributes to the overall security posture of a system. And if that development environment is compromised, or if that code base is compromised, that's another attack vector. So there's a number of unique ways to, quote unquote, pivot into a space system. And those are some of the ways that that we definitely consider during the engineering process. And I'll say it's just a huge challenge out there. There's a lot of attack surface when you start to boil down this into an engineering problem and think about all the environments that when you build a spacecraft and when you launch a spacecraft, all the things that spacecraft touches, whether that's before operations or during operations.
Okay. If you've had some exposure to cyber in a business sense of actually working in an organization, you'll know that it's really risk management. You don't have infinite resources to apply to the cyber problem. You don't have infinite time. You don't have infinite people. The problem can seem infinite sometimes, so you have to sort of triage and prioritize where you're going to put things. And I wrote a white paper not too long ago that was talking about cyber threats to space systems. It's very, very hard if you're talking about a Class A spacecraft to imagine how an adversary would trigger a cyber event, how they would actually inject in the supply chain, how would they make something happen that they wanted bad to happen at the right time in the right way that they wanted. It's hard to imagine how they do that, except if you have very high motivation, if you have a near-peer adversary, if you have lack of attribution. There's all these other characteristics that you have to mix into the risk equation that essentially what the paper says is even though it's very, very hard to attack, you would at least hope that it's very, very hard to attack a major spacecraft via cyber, there's a lot of reasons why people would be trying very hard to do it, and there's some indications that they are. If you just Google up spacecraft cyber events, you'll come up with open source, a few things that have happened over the last few years that you referred to. So I was just going to ask the panelists if you could just comment in general on cyber risks to spacecraft and what we can do to the system, the space system, to make it safer.
Yeah, so I mean, you hit on all the risks there. That there's a number of different avenues to approach where the attack surface is, where the threats might reside. I think from an addressing it standpoint, with a lot of emphasis on really software-defined everything. That's both an attack surface, but it's also an opportunity as well. So some of the issues with legacy platforms are things that we can't change on orbit, but having things that you can change on orbit allows you some flexibility over the life cycle. So those are certainly things that we consider when we're doing engineering, and some of our products are focusing a lot more on the software-defined aspect as a result of that. There's again attack surface in that, but there's also opportunity to mitigate a new threat or increase the effectiveness of a security control, even when the system's in operations. I think you hit on it. The most difficult aspect of space is we can't bring it back down to Earth and fix it. So we have to think creatively about ways that we can update the logic to include security by design over the life cycle of the program.
Yeah, and I would add to that maybe in the terms of resiliency. So the system of systems, if one gets compromised, can that be contained and the rest of the systems kind of take over and just they know to ignore the bad data from one versus the good data from many. So I would say maybe resiliency is a good way to approach this.
I just want to emphasize the system of systems concept here, that there are so many pieces involved in these systems that attacks can come from almost anywhere, and it's important to design the security to be both in depth and breadth. You can't assume that just because the spacecraft is up there and isolated, nobody's going to get to it. And processors can't do much on legacy systems. But as you're designing new systems that have lots of processing power, lots of memory, it's time to start putting the intrusion detection things and so on board, all the different elements of the system, because I don't think it's possible to assume anymore that any one part is not going to be compromised.
And don't forget, when we talk about space, we're not just talking about space satellites and communication satellites. We have people in space. We have robots on other planets. These are also assets that, the United States could be made to look really embarrassed, and that could have huge implications into geopolitics if something goes wrong on the space station because of something we plugged in. University of Colorado rightfully brags about sending things to the space station every other mission. What if something is wrong with what we plug in to the space station, and there's a cyber attack through that vector. So it's not just getting through the link, getting up to a satellite and doing something. It's also, again, there's the human issues, there are spacecraft, there's human lives at risk. So all the same challenges, including the social engineering of the people involved. We know astronauts are not perfect. I mean, there's been, I wouldn't call it a cyber offense from an astronaut on the space station to Earth, right? So, I mean, these things are happening. We're all human. Astronauts, NASA employees are human. That has to be looked at as well.
And I just note on that, you can Google this up, but embarrassingly, there was a USB stick. This is my understanding, is just reading open source stories. A USB stick was taken up the space station off a laptop and infected other systems on the spacecraft, on the ISS space station, and they have since switched to Linux. So I'm going to start with Eric again down here, is that one of the issues with defending space systems is you have links to the ground that you can potentially lose access to do certain things, and it's hard to respond quickly. So classically, the way you command and control a spacecraft is it does some autonomy operations of station keeping and so forth, but mostly from the ground, you tell it, point here, do this, look up, look down. You very specific commanding from the ground. And then if things go wrong, it defaults down to what's called safe mode, which basically says something bad happened, I don't know what it is, I'll call home, and then they'll sort it out and call up. And you'll see that sort of thing happen on the Mars landers and that sort of thing as well. So from an autonomy standpoint, there's this risk of, as we're designing more modern spacecraft that have larger and larger attack surfaces, it's not a very good answer to say, well, if something bad happens from a cyber standpoint, we'll have the spacecraft call home. It may not be able to. And then we'll have the people on the ground figure it out and send up commands eventually to do something, which is usually on a, they go to a conference room and figure it out for hours, and by that time, your spacecraft is destroyed. So I know you work in autonomy, and maybe you could discuss that a little bit, and the other panelists, in terms of how the idea of autonomy fits into defending spacecraft.
Yeah, a great question, and I almost want to say, well, clearly autonomy is not the answer, but would sort of be antithetical to my whole research portfolio. But the point there is, certainly autonomy is an element of defense. I mean, I think the more capable we can make these systems, the more resilient they can be. A big push these days in autonomy is that sort of self-diagnostic, self-healing concept. I think there's absolutely a place for that. I guess the reason why I wanted to say autonomy is not an answer, if you can't talk to a spacecraft, it doesn't matter if it's alive or dead, you can't talk to it. So there are certain challenges that you just won't be able to solve with autonomy. But if a system can recognize it's under attack, if a system can recognize its capabilities have been degraded, then certainly using things like autonomy can help. Now the challenge with autonomy, and really the grand challenge of autonomy right now is, as we research it, is how do you then certify that autonomy? Autonomy is very slow to move into the space domain because of the levels of resiliency and the levels of safety that you need in a spacecraft compared to a self-driving car. And so as much as I want to tell you that, we'll make our spacecraft resilient through autonomy, those are the last domains that get the autonomy, because that autonomy cannot fail. Right? In a car, you got a billion cars, a billion miles, you can find the faults fairly easily. Again, spacecraft, you don't get to go up there and change things really. So it's going to be one of the last domains just because of the level of rigor that has to go into certifying the autonomy or whatever the solution is.
Yeah, so I agree that the more autonomy is needed, because if the system is completely dependent on the ground control station, you've got one very weak link. And does anybody here remember the whole light squared and legato fiascos? So the problem there was GPS operates on a particular frequency, and the FCC sold off a block of spectrum right next to it. And in principle, that wouldn't interfere, but when GPS receivers had a very broad receptive field, and so even though the signal from the light squared system would be very sharp, the receptive field was very broad, and so it was technically going to be able to knock out GPS. And so if it's that easy to knock out something that's that critical to our modern lifestyle, we've got to come up with mechanisms to let the systems operate autonomously.
Yes, and I would agree to go along with the resiliency on that one as well, from what Eric said. Validation. So you mentioned earlier too with like how do we update firmware, how do we update software? That's great to update that, but where's the validation being done to make sure that the firmware you're updating is correct and it hasn't been corrupted or modified in transit or from the time it was created till the time it's being implemented. So along with resiliency, how do we validate these inputs, especially with autonomy? How does it validate its own input it's receiving? How does it validate the input it's receiving from its peers, from its fellow autonomous systems, to make sure that it's not being told or it's not telling itself to do something nefarious or corrupt?
Yeah, I definitely echo that. I think autonomy is a great thing. The trust and the authentication definitely has to be a part of that and engineered into that. So, all the same issues that you brought up is, how do we trust the logic on board? How do we validate that is good and came from a trusted source. And then on top of that, the data that we feed into these autonomous systems, that there has to be a level of assurance that's established through sound cybersecurity principles like authentication and strong encryption properties on that. So it's just one of many solutions to be considered for overall resiliency in the context of how we operate through various types of threats, whether they impact different parts of the system or not.
How many out in the audience, you're familiar with the concept root of trust? Not so much. So particularly in embedded systems, but sometimes you would hear in terms of laptops or so forth, you might have something called a TPM module, Trusted Platform Module. But the idea with root of trust is generally that you have some hardware artifact on a processing system that you use as root of trust to basically always go back to. Maybe it's a secure key storage, it may provide different functions, but essentially it's a way for the processor to validate itself, and then it's also a way for external nodes to validate that that actually is that device. So if you have a device with root of trust and you're across the network and you communicate with it, and you both have root of trust, you're both sort of doing authentication at the hardware level between the devices. And I know at Aerospace we've been doing some root of trust issues, root of trust prototyping for spacecraft. You can use it for software signing and things. There's a lot of things that are just not in any spacecraft right now, but maybe the panel could comment on the idea of root of trust, if you've been experimenting with it, how you think it does or does not apply to spacecraft. So
it absolutely applies. I think it's across the board. What you're seeing in embedded systems is that movement towards built-in root of trust and the ability to validate the bootload, validate code that's running on the processor or on the system on chip. So absolutely a necessary capability. I'd add one of the other big challenges with spacecraft is size, weight, and power. We're always limited in that sense. And then also just the harsh environment of space. We typically deal with much older processing specifications than you would otherwise see, even in aircraft or other embedded platforms. So that's certainly, space is going to be one of the late adopters of some of these technologies just as a result of that. What we're seeing from a standpoint of what vendors are offering on their system of chips or systems on chips is really the ability to do that built into the product. And then certainly, I can say for our company, root of trust is absolutely a point of emphasis for a lot of the embedded technology that we develop.
Not much to add on that one. I think that was pretty robust answers. I would also maybe consider the costs associated with the processing, the additional processing. So what does the root of trust entail? How much additional processing has to happen in order for that validation to take place? And anytime there's additional processing, there's an additional cost. So if we think about encryption, when encryption first became important, or people started doing it more and more, there was a cost associated with it, and that was rudimentary encryption. And now we're looking at longer bit streams, longer encryption keys. That just takes the encryption process that much more additional cycles, additional time. With that then is an additional cost. So given where these assets are, if we're talking about overhead assets, that's an additional cost that has to be considered. But hopefully there's a way to figure out a cheaper and better and a more efficient way to do that.
Wow. So with the increasing, exponentially increasing complexity of systems, it's virtually impossible to check every possible attack path, right? I mean, we know as computer scientists, right, that's kind of equivalent to the halting problem. You're not going to solve it. You can't check everything. But there's also beginning a set of tools that can run over and check known vulnerabilities and so on. There's libraries that MITRE maintains, for example, of known networking vulnerabilities. And it's people are now working on programs that will run through your protocol stack and check to see if any of these vulnerabilities still exist in your system. And we need to be relying on more automated tools like that to double check and triple check everything we're doing to try to prevent anything that we're at least aware of, because there's more things than any human programmer can possibly check.
So I don't personally work with the root of trust in that concept, but I can understand what it is. And when I think about things at the sort of low-level component, computer level when it comes to a spacecraft, I think it's important to just make note, for those of you that aren't space system engineers, that computers are really sensitive to the radiation environment in space. And one of the unique aspects of a spacecraft is the hardware design itself. So it's not just expensive equipment because, it's going up in space and the government can charge lots of money and whatnot. Like, you have to make it radiation tolerant. And so these concepts that we can use in our laptops or in our processing plants or Internet of Things, maybe those concepts will work, but even the simple question of building a device that operates in space that has a root of trust, well, if the bit gets flipped because of radiation in that device, all your computer design, all your computer engineering is still lost because of basic physics. So that's also something that, in this case, complicates a hardware solution, is the hardware doesn't stay static the way we might think of it in a terrestrial application.
Okay. There's sort of a joke in IT that there's the 7-layer communication stack, physical up to application, and above that there's political and management and so forth. And so what I thought we could talk about a little bit is sort of the cultural aspects of adapting to change, to protect things from cyber and space. And just as a quick introduction, I was talking to Ethan before, primarily support the Air Force and very high value asset space systems. I've been doing it for a number of years. I've been doing research for a long time, but I couldn't really engage the customer that this is something we have to deal with before 3-4-ish years ago. And it's completely changed that. In terms of DoD space, no, this is a problem. It's across the space enterprise. We need to put a lot of effort to try to solve it. However, you still have this buy once, use 15-year issue, and it's also pay for once, use 15 years in terms of spacecraft. So it's very difficult to say, well, yeah, we know this was fine 5 years ago, but this is our threat environment now, and we need you to double all the costs that you're spending on security because all these new things have come. And the program manager's like, well, I understand it's bad and I understand the problem, but I was given this amount of money and I have this many years, and so we're kind of struggling with that. So maybe the panelists could, talk about sort of the cultural aspects of trying to get this done.
So, I worry that this is sort of an issue of confirmation bias where I'm more aware of cybersecurity issues, so I see it being discussed more often. But it definitely seems like over the last 5 years, at least in my domain with unmanned aircraft and drones, that at least it's discussed. It's a problem that's identified. I mean, we have TCP because it's a problem as a university we've identified. So putting aside maybe the exact question of the culture of security as it relates to NASA and space, at least I think it's a problem that's being talked about more. You're seeing conferences with sessions on this topic. It's at least something that we're trying not to Band-Aid at the end in all of these systems, even though You've got the drones out there, the self-driving cars out there, the spacecraft are up there. At least we're talking about it, so the culture is starting to be aware of these problems at a minimum. Now, I worry that by talking about it, we also highlight all the problems that we then have to spend the money to hide because no one realizes those vulnerabilities were there. But at least we're having meetings like this, and it's a topic that is more visible than it's been in the past.
So culturally, I don't believe that in many instances, security is one of the things that gets designed into systems. And we in TCP were working on adversarial thinking and trying to get people to think in the design stage about what would a bad guy do to try to break into my system. But as I said before, especially for small companies trying to reach time to market, that's not there yet. And part of what we have to think about politically and culturally is, when do we start having ramifications for failing to put security into your system? Is this something governments need to involve in, or is this something we just leave to the law profession and lawsuits? Because as we put, like you said, tens of thousands of small sats up into space, and they get compromised and are used, as projectile weapons to knock out some critical system. Are there penalties for having your system compromised?
Let's see here. How do I want to answer this one? Okay, so as the trons are starting to create smoke based off of the previous answers, culturally, I'm thinking culturally as it applies to generationally. My parents had a car, and I remember this car because they had it for so many years, right? They had a TV. They had this TV forever. So I think culturally and generationally, I look at now the cell phone that we have. I would bet that everyone in the room has one, and you probably get a new one every 12 months or sooner. The laptops that you have, they have a shelf life of 3 to 4 years. They just stop working after a while after so many upgrades. So culturally, I think you're probably better poised to adapt to security and to be able to change rapidly, or at least faster than our predecessors, than generations before us did, because they were set on this thing. We have this thing. We've got to make it last forever. We've got a satellite system that we have to get 10, 15, 25 years out of. But I think if I can answer that, generationally, it's exciting. I think as I look across the audience, you're probably better poised to adapt a lot faster than my generation or my predecessors, my parents, my grandparents were.
Yeah, I'll just say, coming at it, my role is very on the technical side, not necessarily on the policy or the governance side, but I have to say the technical side is actually the easy part. Given enough cost, right? Given enough money, these are solvable problems. I think culturally and with policy, those are the bigger challenges. Wayne brought up, I think, from a defense perspective, the line of thinking when you go through the systems engineering life cycle is that we're going to build this product starting with a set of requirements. We're going to turn those requirements into an architecture. We're going to turn that into a design and into an implementation, and then we're going to test and make sure the system met all the requirements. Well, in the meantime, over that few year life cycle or more, depending on the system, the threat landscape is completely changed. So we have to figure out a way to create more iterative opportunities where we have the ability to introduce new security measures midway through that design life cycle. That's a huge challenge for especially given that culture, that typical way of acquiring systems. And then the other aspect is on the commercial side, and you mentioned it with time to market. There's tremendous pressure to get a product released, and that pressure doesn't really include security as a result of that. So you've got this other aspect of the forces are really shifting towards we need a product now. I don't care, just make it work, right? Security is not part of make it work. It's security is part of make it work well and make it work as it was intended, and that doesn't always get accounted for in those circumstances. So I know we've had some interesting conversations with NIST, who's very much involved with the standards in cybersecurity. And they're certainly wrestling with the commercial problem as well as how do we govern these CubeSats and experimental satellites that may have larger impacts to military systems or systems that are used for more critical types of operations, right? It's a huge problem, and I think it's the biggest problem in cybersecurity that we face.
Just to build a little bit on something Eric said about, do we really even want to be talking about this and exposing, some potential, weaknesses in this whole industry or so forth? Probably not many cyber specialists here, but if you are, you've probably heard of Black Hat. It's probably the premier sort of hackers conference that's every summer out in Las Vegas. It gets bigger and bigger and bigger. And over several hotels now. And you'll go from conference room to conference room to conference room. This one will say how to hack the ticketing system for your favorite airline. The next one will say how to hack the phone in gas stations. The next one will have how to hack the military system on this. And basically, it's the model of we're going to expose it out there. We're going to tell the whole world that there's a vulnerability that I found in your system, and that's good because Cisco or Department of Defense or somebody will go fix that right away. Well, amazingly, sometimes it's not so much right away, but it does get fixed. And that's kind of the model that they have that has actually seemed to work pretty well. It's the open source model that you expose vulnerabilities to the world and people fix them. So it's generally thought that open source code is actually fairly secure because it's had so many hands touch it, right? And it's been evaluated by so many hands. And so I think we're kind of searching for the right place in terms of space systems. Obviously, we're not going to have a conference. We're going to go, how to hack GPS satellite. And then the next one's how to, we're not going to do that. But in terms of general terms of talking about this is something that needs to be addressed and sort of evangelizing that, I've been doing it for a while. I think it's a great career track. If you're looking for something to do for a thesis, there's a lot of open topics here. And what I was going to do now is just open it up to the audience if you had some questions for the panel. Anybody? Yes.
So you've talked a lot about this in different ways about how do you deal with something that's going to be in space for 15 years, and you probably freeze the design 5 years before that potentially, depending on how big it is. So how do you get your engineers and designers in a mindset of predicting something that's 20 years in the future? I mean, if you're in the year 1995 and you try to predict the cybersecurity landscape of 2020, I doubt you would have gotten it very right. Maybe you guys would, but do you focus on that, or do you focus on being able to completely revamp the system while it's up there by uploading new stuff to deal with the new environment?
So from our perspective, I think it's both. So there's definitely techniques that we use, threat modeling, attack trees. There's a number of different processes that we try to use to really. Cyber tabletops are another avenue that we use, but we really put a lot of effort into predicting what could the system be vulnerable to, what would the impacts of those potential vulnerabilities or weaknesses be, and try to engineer that from the start. And obviously that's a fairly new thing I know for Lockheed Martin and really for industry to think that way, think adversarially from the start. And try to predict what the attack surface is going to be. And then the other side of that too is really architecting for resiliency. Like I think a lot of people have said here, try to consider ways to design a system such that it can be changed or can adapt depending on the different attack surface avenues or attack vectors or vulnerabilities that may come up. Think about put a lot of effort, I would say, into an architecture that can adapt to those types of things or can protect areas that we may perceive as weaker from a security perspective. So there's certainly architecture techniques, and then I think there's processes that you absolutely have to follow from the start to be able to be successful in really engineering for the future.
Anybody else want to put in?
I just want to emphasize this concept of adversarial thinking that we've been talking about. I think that's one of the things that attracted me and I think is very unique about TCP. I know from my experience working in Department of Defense, we'd have brainstorming sessions about systems and how, okay, what do we do to counter them? And you can learn this mindset of trying to think like an attacker and thinking of where the vulnerabilities are. And you won't get everything, because obviously the technology is going to change. But you still can make your system much more resilient. And with a really well-designed architecture that you've subjected the adversarial thinking and looked and examined, can I upgrade these parts of the systems that are most likely to be attacked? That's going to make the system much more powerful and resilient in the end.
Unfortunately, though, to go back to your question, you can predict with the best models and have the best intentions and or attempt to put the best security in place. Ultimately, it comes down to cost. So are you able to? So I could build a castle wall around this CubeSat. Doesn't mean I can deploy it and still make it operational. So at some point, security becomes a hindrance. And at some point, I think the risk models and the other threat modeling comes into play, and you just have to make a decision and press. Unfortunately, that may leave vulnerabilities. That's part of the risk model. You just have to accept those.
Yeah, just to add on that, you're not going to fix everything. That's just the reality. But yeah, like you said, risk modeling and understanding the level of risk that you can tolerate and making sure that you're designing to that is important.
Another question back there.
Yeah, I wanted to go back to the policy side of things. We talked about culture, and we talked about standards. Standards are not necessarily policy, but they can be built into policy. And what I'm really getting at is, basically there are really only a handful of significant federal legislation addressing cybersecurity. Two of those have to do with just managing data and reporting data breaches. So, there's nothing compelling industry, commercial entities towards any specific cybersecurity outcome that I'm at least aware of, unless they're working in a military, civilian kind of context, and then government regulations kick in. So what I'm really wondering is, for a lot of the challenges we're talking about, separate from the technical solutions, in your observation, do you think there needs to be more compulsion towards people, towards actors doing something, or is sort of the voluntary rules that we sort of have, on the books now, is that a more effective regime?
I guess I want to comment a little bit just in terms of my anecdotal experience, not just with space systems, but with power grid systems and things of that nature, is right now the government tends to come in and look at all these various systems, and there is some oversight now, and they'll, bad, your security is just awful, right? But they won't necessarily come with pre-built solution that's affordable that, well, plug this in and we'll be happy, right? And so a lot of times when you have a problem, you have to decide, well, what is it, a technical problem, is it a management problem or whatever. I think there's actually a leadership, in my opinion, there's a leadership problem in the nation in terms of not just evaluating the badness of all these various systems from space to energy to retail, but to actually fund repeatable solutions that can be deployed by a number of different vendors to some particular standard, so that you're not just levying a requirement. That's the state we are in. We have a lot of requirements being leveled of, you have to be cybersecurity, you have to do monitoring and metering, you have to do all these things, but you get to figure out where to find the money, and you get to figure out how to do it, even though you don't have the money to hire all these SMEs. And if you did have the money, you can't find them because they're all working for Google, right? So it's a challenge what I think needs some top-end solutions, in my opinion. But
yeah, I'd agree with that. I think I see it a lot too. When you look at how assessors view systems, it is adversarial. It's very much, you did something bad, it's punitive. And I've seen that lack a lot of effectiveness in terms of how do we get to a real solution here that makes sense from a cost standpoint and all the other factors that play into that. And it's hard for me to comment on the commercial side in terms of how you fix that. There's certainly been a lot of discussion as to what's the right path. Is it legal? Is it standards? Is it requirements? But ultimately, I think, yeah, it comes down to technical solutions that can work across the board for industry, because I think that it's very unappealing for to levy requirements that industry isn't ready for and doesn't have solutions that are made for the problem that they're trying to solve. And so I think all those options I think are kind of on the table at this point, but the technical solutions and having those be kind of commonized and having somebody really help industry with that, I think would be a great thing.
I think it's an excellent question, and it opens up the door to a topic of economics of cybersecurity. And I'm not the smartest person to talk about that. I know that at some point somebody's going to absorb the cost associated with policy, changes in policy. A lot of times that comes right down to the consumer. I know my Netflix subscription went up like $3 a month back in about a year ago or so, and I think my Pandora now, my satellite radio or yeah, everybody's fees go up. So that I can't speak for fact, but I would imagine that there's that's associated with policy at some level, and as we include more cybersecurity policies, somebody's got to pick up the tab for that, and we just have to absorb that in order to implement it.
And part of the policy creates incentives and disincentives for companies. And just creating a government policy that's too prescriptive would likely have very adverse effects. But somehow we need to have a cultural awareness of the need for security. My analogy is always, with secure cars, for example. Are you willing to pay $500 more because it's secure? So where does, what's the line for the consumer where security is now important enough that you're going to be willing to pay that price for it?
See, I think your question actually maybe has the opposite of what you may have been intending for. I think if you give people the option of paying $500, they won't. We were actually talking earlier, but they should, right? So we were talking earlier about our cell phones, and I don't do two-factor authentication on things, and I know I should. I shouldn't tell you all this, right? I don't have like great passwords on all my accounts, right? And I feel like I know better, but even then, when it comes to some of these security issues and privacy issues, I don't know. I have this like herd vaccine mentality, right? Like if my credit card gets hacked, like Visa will be hacked, and they'll figure it out for everybody, not just me. And so I feel like that's a very easy attitude to take. That's very dangerous. So I think we need policies to make sure that this is thought through. We've already said earlier, we're not thinking about it enough, the culture needs to change. Like, I'm happy to have some higher level agencies say, you need to think on this. Understanding that the economics and bad's not helpful, but it's better than keeping our heads in the sand without someone, really urging us to think about it.
Can I read that
Yeah.
Got me thinking. So yeah, what was that ninth layer in the model?
Politics.
Politics. So bring in the policy, and the adversary, it can maneuver, and they are a lot more agile than any bureaucracy associated with policy is. So we can implement new policy, but by the time it gets implemented, it's already outdated. Unfortunately, that's just kind of the way things go.
All right. Any other questions? Here's one.
So, first of all, thank you all. Technology, cybersecurity policy, yeah. Why shouldn't we all be frightened? Because it sounds to me like there's exponentially growing problems. We're always lagging behind the exponential front. So we lose. So why should we not expect GPS and all of the rest of these systems to just collapse and fall into a fetal ball?
It's really hard to get into those systems. It's not impossible. We're trying to address it. We're not trying to say the sky is falling. We're just saying these are serious. We need to look at these things. And honestly, right now, if I was king for the day and I was trying to address security, all these general purpose operating systems where you've got like the Kanji key set on your Windows machine or something, or all this code you don't use that's attack surface, right? If I was king for the day, it's like, no, this is the code I use, and so I'm going to use that code, not this code, right? That kind of goes across the board. But it's working. Do people have their bank accounts hacked? Yeah, or do you hear about some new exfil about every day? So I think it's rather annoying that I work in cybersecurity and I've gotten about a dozen letters over the last 5 years of congratulations, you've been hacked, and from this, and my wife lost her credit cards and so forth. But the risk payoff, it seems to be okay now, right? There's a lot of cybercrime, there's a lot of bad stuff happening. The Microsoft, other vendors, Institute of Space, everybody's trying to make things better and better, and it's cat and mouse. They add a patch, they figure it out. I mean, Windows 10 is pretty secure, but that's today, not 5 years from now. But it seems to go okay. Everybody's using their stuff. There's, billions of IP addresses now. Most of them work just fine. There's a lot of bad stuff happening, but as we move into cars and things more, it gets a little bit scarier when cyber can bring down a plane more easily and that kind of thing. But it seems to be okay. The sky's not falling. People are doing their work. But.
We become desensitized. So we accept the use and the convenience in lieu of the risk. I went out and bought a Jeep a month after Charlie Brown drove it into a ditch, remotely, hacking the car. We've become desensitized to it, I think.
So society has its own natural trade-off, right? I mean, when crime goes up, you pay more to get more police. When crime goes down and you're paying a lot for a police force, you reduce the size of the police force until society reaches a balance that it's happy with. Okay, so I think we're in a good place now, but part of what, I'd like to get across, you guys are the future designers. And, I want to get you in this mindset of thinking of these problems before they become problems, before society has to do the weighing off. So we start thinking about these things in the design of our systems.
So Wayne started this whole panel by mentioning this concept of a day without space, and I thought we might get to spend more time on the doom and gloom of what happens if we don't solve this problem. So I'm glad you brought it up. And maybe a thought experiment, what does happen if we have a day or 2 or 3 without space? But I think to your point is we're stressing the importance of this so that you all will work on it. I mean, I think this is why we shouldn't feel so much doom and gloom, is that we're being aware now, we're building a workforce that can address these issues, and we will, whack down these problems as they come. And it's important to understand the risks and why we do this. And I think that's maybe the parting shot I'll take is just envision that day without space and make sure you are aware of why we need to do this.
Yeah, so I would echo that. It's not being scared necessarily. It's being aware and understanding, what techniques, what technical concepts and approaches we can use to solve these problems, because they are solvable. There's a number of solutions out there that various industries and other places have put to bear. So we know we can do this. It's just a matter of being aware and turning that awareness into action, and especially considering how cyber presents a risk and how we can address it.
Okay, all right. Thanks, everyone.
So, let me thank Garrett, who helped facilitate, make this all happen. So thank you, Garrett. Technology, cybersecurity, and policy. Everybody, technology, cybersecurity, and policy. Thank the panelists, please.